Sí.
Do you want to start? Are you ready?
Yes, I'm ready.
Okay, start when you want.
Can you see the full screen?
Yes, we can see your screen and we can hear you.
Okay, so let's go.
Well, the sound is not great. Try to speak a bit.
Is it better now?
I think so. Yes, it is better. Okay, go ahead.
Okay, so here it is. So hello everybody, good morning, and I would like to thank Asuncion and all the organizers for this workshop, which I find very interesting because focused and but exploring a broad range of environments. So in this talk I will focus on the gas phase sulfur in prestellar cores. So we are moving toward the dense ISM and the early stages of star formation. So the outline is I will briefly present the context, which is I think well known from everybody, but which is that of the depletion of sulfur in high density regions of the ISM. And then I will will move toward the work that I will present here, which is the observation of nitrogen sulfide in dense cores in the Taurus cloud. And in doing so, I will try to explain how we can use the NH over N2H plus abundance ratio to measure directly the atomic sulfur abundance in dense cores. And then we will realize that the main carrier of sulfur in the gas phase, when it is not depleted, is actually neutral atomic sulfur. So a brief review. Stellar nucleosynthesis produces the atoms that are incorporated in molecular clouds. And once produced, those atoms can be in, broadly speaking, two phases. A refractory phase, which is really a solid phase, which resists high temperatures in the ISM, and volatiles. And volatiles mean gas plus ice. And provided that you don't break your grains like in shots, then these two reservoirs are disjoint, and the amount of volatiles is constant for a given element. And obviously you can have exchanges between gas and ice. I mean, we've had a lot of talks about that. And the various elements have different propensities towards depletion into refractories. This was basically the work of Ed Jenkins in 2009. For sulfur, the total sulfur abundance is 14 ppm. This is the value from Daphne et al. 2009. And I like to quote this value because it is obtained from the atmosphere of B main sequence stars in the Orion association. B stars are young stars. So this really reflects the ISM as it is now, today, here in the galaxy. And the fact that it is consistent with the solar value may indicate that there was no significant chemical evolution, at least for sulfur, in the solar neighborhood of 4.6 gigayears. So regarding the sulfur budget, the study of Jenkins 2009 showed that sulfur has no propensity toward depletion into the refractory phase, which means that the volatile abundance of sulfur is equal to 14 ppm. And in the diffuse ISM, where you don't expect ice, then the gas is equal to the volatile, which is equal to the total. And this was confirmed by Javier Goicoechea in the Orion bar, as we saw yesterday. And however, it is very difficult to follow the reservoirs in the ISM and especially in the dense ISM. And this is true in general and for sulfur in particular. And in the dense ISM, it is really tricky to infer the bulk from the trace species, because often the main carrier is not observable. This is true for sulfur or nitrogen, for instance. In the diffuse ISM, S plus is observable, and this is the main carrier. I put here a brief review of measurements of the abundances of sulfur-bearing species from translucent to dense gas and in low mass versus high mass. So on the left table, you have from the last and Cassidy paper, 2019, some values for those usual suspects of sulfur-bearing species in diffuse, translucent, and dense clouds. So translucent is somewhat intermediate between diffuse and dense with respect to the extinction in at visual wavelength. But we have to keep in mind that all these is very dynamic. I mean, the ISM molecular clouds are transient structures. Okay, and on that table you have measurements in the dense TMC1 CP. So this was reviewed in the dense key program. We'll see that later on. But obviously, what you can see is that there are important variations from translucent to dense, and there are also variations from low mass on the left to high mass. And especially if you look at, for instance, NS, here you see that the abundance of NS is of the order of 1 or lower in 10 to the minus 11, whereas it is for 10 to the minus 10 in these low mass environments. And there are other differences. Okay, and so within a large scale environment, you can also have differences. And this was shown by the GEMS key program, stressing the influence of the environment parameters like the density, cosmic ray ionization rate, or the extinction. So I put ranges of values. So within the torus, you have variations which can span 2 decades, really emphasizing the influence of the environment parameters. There are some instances where you can directly measure atomic sulfur, and this was the case in that paper by Anderson in 2013, where they were able to detect the fine structure line of sulfur at 25 micron with a Spitzer satellite. And their result was, well, I mean, the study is a tricky one because it is difficult to disentangle the sources of emission of sulfur. It could be the J shock or the C shock. And obviously you don't expect the same mechanisms of release in either shock. But I mean, conservative assumptions lead to the result that atomic sulfur should represent up to 10% of the total sulfur. And okay, so there was a trend towards having high amount of atomic sulfur in the gas. So what we may call the depletion issue is an old one, obviously, and it started, as far as I know, in that paper by Tieftrunk in '94, well, based on earlier studies, obviously, but summing the S-bearing species was amounting for not more than 1% of the total amount of sulfur. So the question was really, where is sulfur? And not all models agree with that respect, and some models, well, in the last year there has been a lot of review about the chemical reactions, and there is this Vidal et al. Paper in 2017 showing that we don't expect strong depletion of sulfur, actually. And this was sort of the same result in the last and Casely paper, showing that depletion occurs after 1 million years. But where models start to really disagree now is in which form you should find this depleted sulfur. And some models predict that solid H2S is the target. But this was found negligible in the last and Casely paper, 2019. And based on observation and comparison between observation and well, the state-of-art observation of the GEM survey and chemical models, it was found that the S over H, well, S over H means that really the amount of atomic sulfur in the gas phase was something like 0.8 ppm, which represents a depletion factor of 20 in the translucent part of the TMC1 cloud, whereas depletion was 10 times higher in the dense part of TMC1. So it really appears that depletion increases from translucent to dense. On the other hand, and this was reviewed earlier on in the previous talks yesterday and before yesterday, I mean, so far only OCS in ices has been detected at a level which is really, really low. And we expect that the James Webb will really renew that field. So historically, the amount of sulfur was usually used to be very low in the models, and this was the so-called low metal and high metal abundances. And this gets back to 1982, and the real reason to deplete by a factor of 100 was to match the ionization fraction in the dense ISM, which was based on DCO plus, expected to be 0.01 ppm up to 1 ppm. So there was actually no other motivation than that of reproducing the ionization fraction to deplete by a factor of 100 sulfur and other metals. And we still find these low and high metal abundances in the literature. So let's move on now toward the gas phase sulfur in dense cores, so which is the present study. So we've been studying 4 cores which are located in a single large-scale environment, which is the torus. And those 4 cores span a range of densities. So their nicknames are in the LINS catalog is L1544, 29E, 29B, and 1498. And as you can see, this is a map, a large-scale dust emission map obtained with the Herschel satellite at 500 micron, this one. And you can already see that those cores are different. And well, they look like different. And if you look at them in more details, which you can see on the right, well, you can see that there are one, L1544, which is well isolated, and 1498 also, and L1521B has sort of well, not well-defined shape. And so our observations were targeting several positions in each core. We didn't make a map, but we targeted 20 arcsecond offsets positions. And what we have been observing are a bunch of lines of nitrogen sulfide. So nitrogen sulfide has a rich spectrum because there is lambda doubling and hyperfine splitting. And well, which is good and bad news. The bad news is that the intensity is split into a large number of lines. And the good news is that you have several lines which are very close in frequency. And well, the problem with NS is the frequency. As you can see, it is 115 gigahertz. And for those who know, this is very close to the edge, the upper edge of the atmospheric window, 3 millimeter window. So the opacity is dominated by molecular oxygen. So there is nothing you can do with this. So the observations were done with the 30-meter telescope, which is located in Sierra Nevada near the Alpujarras. So this is why I put this Plateau Alpujareño, for those who know. And we've been using the Emil receivers and the Vespa autocorrelator spectrometer. And the typical system temperature is 300 K, which is quite high with respect to the Emil receiver, but this is due to the oxygen, atmospheric oxygen. So here are the spectra for the four sources. And well, as you can see, the detection rate is high. And in fact, it was detected in all sources, and the fluids at half maximum are not so low. And in particular, we cannot extract any useful constraint on the temperature. But so, and furthermore, the line ratios are often nearly theoretical, which means, I mean, these are the theoretical line ratios for the hyperfine ratios, purely based on spectroscopic properties. So that indicates already that the optical depths cannot be so large, and that maybe a single excitation temperature is is a good approximation. However, we did not assume a single excitation temperature. We could do non-LT level population calculations because we had a hyperfine rate coefficient for the collisions of NS with helium, which was scaled up to the NH2 coefficients. And so we've used the RADEX, which is an escape probability formalism radiative transfer code, to solve for the level populations. That code doesn't treat hyperfine overlap, but we do not expect that to be critical because the optical depth is probably low enough. And then we've been exploring the parameter space, which is density, kinetic temperature, and column density of NS. And the minimization was done using the Markov chain Monte Carlo approach, using the MCEE public primer. So here are some results about the column density of NS. So here in that source, in that case, L1498. Well, so what you can see in this plot is the three parameters: kinetic temperature, collider density, and NS column density, and the correlation between those parameters. And as you can see, the kinetic temperature is not constrained at all. The collider density is loosely constrained, and the column density is quite well constrained. And you see the relationship, the degeneracy between those parameters. And in fact, what this diagram, for instance, shows is that a low density corresponds to a high column density, whereas a higher collider density corresponds to a lower column density. This is usual degeneracy, well, when you have degeneracy. But the important message here is that the column density was quite well constrained, and it is of the order of 12 to 12.3 dex. And the H2 density is also consistent with the expected values from the literature, which are around 10 to the 5 per cubic centimeter. This is another example of degenerate solutions. So in these plots, you can clearly see that the column density and the density are degenerate. And you recover this low density, high column density, and high density, low column density solutions. So in that instance, based on the upper limit, conservative upper limit of a few 10 to the 5, this was the solution which was preferred, whereas here there is no solution, but only a lower limit of the column density. So here are the results for the four sources, and so in that source we have mostly lower limit on the column density of NS, whereas here we have good constraints. And these results, in fact, are in harmony with the very early, well, the first measurements of NS in the ISM, which were due to McGonigal 94. And the column density are very close to the values that we find here. And their approach was an LTE calculation. Now, and this is not the main aim of that study, but we would like to extract some abundances from those column densities. And now you need to compute a nitrogen column density to compute the abundance as a ratio of their column density. So to do that, we've been using the Herschel maps at 3 wavelengths, and sometimes we also had some additional data at 160 microns and at 1.3 millimeter for IRAM. And this was, the usual type of minimization, trying to find the dust temperature, the dust column density, and the spectral index. So the fits are good, but the uncertainties are, for those who have been practicing this kind of game, you know that the mass absorption coefficient and spectral index are always, they may depend on the temperature, and this is not included in this kind of fitting. So now, why should we worry about NS, which is really a trace species? And why should we go to the NS over N2H plus ratio to measure the S over H? So let's look at the chemical network. So it was reviewed according to the latest databases, KIDA in particular. So NS is primarily formed by S reacting with NH and N reacting with SH. And it is destroyed by NS reacting with oxygen and carbon. So it is quite simple, and it is the fact that it is destroyed by oxygen and carbon makes the NS abundance sensitive to the C/R ratio. This was already pointed out by McGonigal and by Sonichar earlier with their detection of NS plus. And then, as you can see, NH is a game player here. And the idea behind using N2H plus is that NH, what we know in the dense system, is that NH is produced by a dissociative recombination of N2H plus. The contribution of desorption is really unclear and not needed to reproduce the amount of NH. So this is essentially the reason why we would like to measure NS over N2H plus. Both species are observable, and NS will trace S, whereas N2H plus will trace NH. And then you can try to compute steady state abundances and derive some analytical relations. And so what you find, well, assuming that the C/R is low enough, because you have the C/R occurring here in the bracket. So if you have good reasons to neglect this term, then you find that atomic sulfur abundance is directly related to NS times O divided by NH. And NH is given directly from N2H plus. So really, the abundance of atomic sulfur can be recovered from the NS over N2H plus ratio, provided what? Provided that you know the amount of oxygen and electrons. And those who know that this is tricky matter. And okay, so for oxygen and trying to go further in our analytical relations, we made very simple, simple assumptions, but I think reasonable. And I can detail that if you wish, but so we adopt an oxygen abundance, atomic oxygen abundance of 37 ppm doing this simple math. And you end up with this relation here, that atomic sulfur is proportional to the ratio NS over N2H plus. The bracket term here just reflects the amount of electrons. So if you can measure NS over N2H plus abundance ratio, then you can measure the amount of atomic sulfur. This is the message of that equation. So we've been checking these analytical results with a grid of models, and a grid of models spanning a wide range of parameters. In particular, we've been varying the C over rho ratio from 0.4 to 1.2 by keeping C plus fixed, but changing the amount of oxygen, because this is the primary source of uncertainty. And we've been varying the amount of S plus, which is the initial form of sulfur in the gas phase. And also we've been varying the density, so 10 to the 4 and 10 to the 5 per cubic centimeter, and also zeta, the cosmic ray decision parameter, from 1 to 10, times 10 to the minus 17 per se. So in this plot, we simply show the amount of atomic sulfur versus the NaS over N2H plus ratio, and what you can see is that well, these are the analytical relations for a bracket term for a zeta over n being 0.1, 1, and 10, just reflecting the parameter space. And these are the measures, well, the measurements, no, the model results. So you can see that, in fact, despite our approximations, it is there is very good agreement. Oh, sorry. So now let's put everything together, namely the observations and the models. So let's look at this panel here with a density of N4, which means 10 to the 4 cubic centimeter, and I've lost the cursor, yes, and zeta of 3 times 10 to the minus 70. So what you can see in this plot, the ordinate is the NaS over N2H plus ratio, and the abscissa is the total amount of sulfur in the gas phase in our models. So the markers, the points, are the results of the models, and the gray bands, the hashed band, are the observations with their uncertainty. So what you can readily see is that the NaS over N2H plus ratio is high in L1521E, which is at the top, and the lowest in L1544. There is only a lower limit for L1521B and detections and measurement for L1498, which is intermediate between the other two sources. And when you compare this NaS over N2H plus ratio with the results of the models, then you realize that L1521E is best reproduced by models with undepleted sulfur, 10 ppm or so. And whereas at the other extreme, L1544 requires a depletion by a factor of 100, which is in harmony with the results from 19 in the dense part of TMC1, the depletion factor of 100. And the black straight line is our analytical relation, assuming that S gas, the total amount of sulfur, is actually atomic sulfur. So what you have here is that in L1521E you have two birds with one stone, is that you first see that in L1521E sulfur is not depleted and it is atomic. So the other panels show the various models in terms of density and ionization rate by cosmic ray. And the conclusions are obviously slightly different. The conclusion is not changed. The values may be different. But you have to keep in mind that those results depend on the C over rho ratio. And provided that the C over rho ratio remains below 0.8, you have consistent results throughout the grid. So these are the main results and summary. So we've been observing cores located in the same large-scale environments in order to mitigate the impact of environmental parameters, which we know are important. And we've been studying the NS over N2H plus abundance ratio and showing that it can serve to measure the amount of atomic sulfur in the gas phase. And the main result is two. There are two main results. First, that neutral atomic sulfur is the main gas phase carrier in the non-depleted stages of evolution. And second, that the depletion of sulfur increases with the evolutionary stage. We have some tentative variations of the amount of atomic sulfur within L44, but it is not clear whether this is due to desorption or depletion. Well, I skip this. So future works include N2H plus detection and L1521B to convert this lower limit into a measurement, into an actual measurement. Obviously, the next step would be to enlarge the source sample and to prospect other large-scale environments like they did in the GEMS survey. Well, chemical models need to be explored in a more comprehensive way, adding more species, for instance, and also following the collapse, of course. So what is the behavior when you follow the chemistry in a collapsing core? We could provide a method to test the prediction from Rodriguez-Barras 21 that the S over H ratio depends on the density as almost 1 over square root of the density. And obviously, it would be interesting to compare with the result from the GEMS study. So thank you for your attention, and please for questions.
Thanks, Pierre. Thanks for this nice talk. I think that indeed it would be very interesting to compare with the GEMS data. Okay, times for question. You should come here. Oh,
Hello, Pierre. This is Nuria. I have a question about how do you obtain the column density of N2H plus, because I guess you may have it may be optically thick. So are you using the 15N isotopologues, because then you also have fractionation on the 15N column densities?
Thanks for pointing this, because I did not mention. We're using literature values, and for L1498, we've been using the results by Tataya et al., which made a Monte Carlo modeling of N2H plus in that source. And then for L1544, we've been relying on the study of Pizzucchi et al., which is also a non-LT model calculation, which was confirmed, in fact, with models by Fabien Daniel et al., including line overlap. For L1521B, well, there is no detection, so this was our lower limit. And for L1521E, this was yielding results from Iroda et al. So we've not been observing ourselves in N2H plus here. So that's a good point.
Or maybe you can also try N2D plus. I don't know which one is better constrained, the fractionation on the deuterium or the 15N. I don't know.
I think that the deuterium is perhaps better understood. But I think that, I mean, for the Tafaya and Daniel studies and Pizzucchi study, we can really rely on those studies because they've been including line overlap effects. So I really trust those measurements of the column density. But you're right, this can be very tricky for N2H plus. Indeed, this was one of the reasons I used those studies.
Okay, thank you, Pierre.
Hi, Pierre. So thanks for the talk. So I have a question, well, two questions. Maybe you mentioned one of them, but I did not realize. So in the beginning, you said that you had several pointings for the 4 different cores, but in the end, you present just results for one value for each one of the cores. Do you see some kind of variability along these different cores? Okay, you're going to the slide maybe. Yeah.
So yes, you're right. I mean, so the only source where we have tentative variations of the sulfur abundance is L1544. For the other ones, we cannot say. We don't see significant variations of that. I mean, there are too large uncertainties on our ratio measurement.
Okay, yeah.
But for L1544, there is a hint of depletion increasing towards the center with respect to the 4 positions around. However, the increase of NS when you go outwards also coincides with an increase of NO in that source. So it is, and so it could be related to desorption or to some mechanism for formation of complex organic molecules. So this is why I say that it is not clear whether this is due to some desorption or to, desorption at that location, which is around 4,000 AU from the center, or whether it is a signature of depletion towards the center. This is not clear at that point.
Yeah, and following with this and related to what Nuria was asking before, so then I understand for N2H plus you also have several pointings. So in these previous observations there were maps or several pointings?
Yeah, absolutely. I mean, L1544 was studied by Bizocchi et al. 2013, and they have a map.
Okay, and one last question, if I can. So when you were showing the results of the Radex analysis, so the kinetic temperature and the volume density were not that well constrained, and then the column density seems to be a little bit better constrained, but of course it may depend on the final volume density, right, that the core may have. So I wonder if, could you observe more transitions of NS to try to better constrain this, and if so, which ones?
Okay, so very good point. So in that study, we only had 2 millimeter lines in very few cases. And it is clear that these lines enables, well, to break the degeneracy. So it is foreseen to observe that the 160 gigahertz lines. So that's a very good point. I mean, I would really suggest to go for both 3 and 2 millimeter set of lines to break the degeneracy.
Okay, yeah, thank you.
Well, I have a question myself, because if I remember well, I think that NS is detected in comets. I think, if I am not, it is not true, in comet. No, NS, nitrogen sulfide is detected in comets. Okay. So, do you think that we can have a formation path on the grain surface or something like that?
Well, I must say that I would expect that sulfur sticking on a grain would first react with hydrogen, but I mean, no, I don't know that. I'm sure that people in the room have much better understanding than I do, but yeah, well, I don't know.
Well, we have people in the room. Francois, do you think that NS can be formed in the ice or nitrogen sulfide?
Yes, I think it could be formed in the ice, but This is not exactly the way I saw to it. For sure, you will see in Rebecca Pitt's talk that NS is a player on solid state chemistry of sulfur. Actually, it attracts a lot the sulfur, and it's a problem. So I asked Jean-Christophe Loison at the rescue, and we discussed this point. So NS in the solid phase is also a big player, even as you said, it's a trace. So this trace is important. So I think NS is a key molecule for the sulfur chemistry, also because it can divert a lot of the chemical pathways. So I don't know if I answered your question, but I agree. NS is a key player. Actually, we do not think about it, but it's quite often detected, and at least in experiments, it's a messy player.
Thank you.
Very interesting. Thank you.
Any other question? Okay, Pierre, I think that there are no more questions. Thank you very much
Thanks a lot, everybody.
for joining us. And I hope to see you soon,
Yeah.
to meet you soon.
I hope so.
Bye-bye.
done within the GEMS project. In particular, this is a sulfur project with observation from different star-forming regions, studying in particular emission from theoformaldehyde and its deuterated versions. Apart from that, I will also briefly introduce some of results at the end of these presentations obtained by Marina Rodriguez, who for personal reasons couldn't be here to present her results. I will talk in particular about the presence of H2S in starless cores. So, as probably everybody knows already very well, GEMS is an IRAM large program granted with more than 400 hours time of telescope time, with, in particular, with the 30-meter scale telescope in Granada in the south of Spain. This project that started in 2017 has as one of its main goals the determination of the depletion of these elements as a function of the visual extinction and in a set of prototypical star-forming filaments. Apart from that, as an intermediate product, GEMS also aims to provide a complete data molecular set of several molecules, including high spectroscopic observation of molecules containing sulfur. In particular, this data set constitutes the best data set that we have with this kind of molecules containing sulfur up to date in dark clouds so far. So it represents a keystone to progress in our knowledge about sulfur chemistry. Why sulfur? I mean, why we are choosing this element? There are a lot of elements very interested. Why this one in particular? This is for several reasons. First of them, sulfur is an ubiquitous element in the universe, and it's also an essential element to all life forms that we know. For instance, in the Earth, sulfur supports several ways of life. In particular, for example, it acts as a nutrient of plants and animals, and is a vital component for some proteins that form amino acids. Here in this part of the slide, I show you a couple of examples of these amino acids containing sulfur. On the left, we have methionine, that is an essential amino acid that we obtain only through our diets. And on the right, cysteine, that is not an essential amino acid because it's obtained through this one, but still you see that both contain sulfur. If we go to the universe, we find that sulfur is the 10th most abundant element in the universe, and also it has a very rich chemistry. In particular, molecules containing sulfur has been traditionally used in order to study star-forming regions, especially affected, for example, for shocks. This is what happens in those regions when we find, for instance, the presence of outflows. We highlight as well that sulfur is especially sensitive to physical and chemical changes during the lifetime of hot core and hot corinos. For all this together makes sulfur as a good element in order to study star-forming regions. Apart from that, I think that sulfur has an important characteristic, and is that it has been measured to be significantly depleted in molecular clouds in comparison with another kind of environments, like for example, diffuse clouds, H2 regions, or the solar photosphere. So where is this missing sulfur? We can ask. One of the options is that it's locked into ices. The problem is that up to date, we have only reported the presence of a few solid molecules containing sulfur, like for example, OCS, or tentatively the detection of SO2. Another option that we find is that this missing sulfur can be as a refractory material or as a volatile molecules. But still the mystery continues, so I think that this is an extra reason in order to study sulfur chemistry. So as I have mentioned at the beginning of my presentations, I'm going to focus in this work in the emission of theoformaldehyde, H2CS, and its deuterated version, HTCS and D2CS. And we have studied these molecules in a sample of starless cores located in 3 different regions of the sky, Taurus, Perseus, and in Orion. Here I show you the list of the starless cores that we have considered in the sample, their coordinates, the molecular clouds where they are located, and also the regions where they belong to. So we have chosen this sample because the regions hosting these starless cores are characterized by different physical properties and for different star-forming activity. So that means that if we compare starless cores in the same filament, we are going to be able to study the evolutionary time effects on these starless cores. By contrast, if we compare, for example, starless cores located in different regions, we are going to also study the effects of the environmental condition in the sulfur chemistry of these starless cores. You can see here a map of the filament that we have considered for Taurus, in particular the B213 filaments, where 5 starless cores indicated with red marks that are located toward the north of this filament, and another 3 starless cores located more toward the south of this filament. In the case of Perseus, this is a picture obtained by Hatchell and collaborators in 2005, but it's very useful because it shows you the whole complex of Perseus with the different molecular clouds that it contains. In our study, what we are considering is two molecular clouds located more toward the northeast of Perseus, in particular B5, Barnard 5, and HH211, and another 2 molecular clouds located more into the southwest of Perseus, NGC 1333 and L1448. Here you see also maps of these 4 molecular clouds where we compare the starless cores located here with red marks. I have not mentioned, but the white triangles are positions of this molecular class where we also have 30 meters observations, but since they are not starless cores, we are not considering them in our sample. And finally, for Orion, where we have considered in this molecular cloud, that is Orion A, 3 starless cores in our sample. So, in order to analyze the emission of these 3 molecules, H2CS, HDS, and D2CS, we have considered the radiative transfer curve RADES developed by Floris van der Tak in 2007. Here I show you the fractional abundances for these 3 molecules in Taurus, first row, in Perseus in the middle, and in the last row, results for Orion. If we observe first fractional abundances for thioformaldehyde, we observe that we obtain the highest value in Taurus for this starless cores, that is B213C5, in Perseus for this one, that is L1448, and in Orion, we find the highest value for the starless cores ORIC2. We have to mention that these highest values that we obtain for H2CS are at least 1.5 times higher than the fractional abundances that we obtain for the rest of the starless cores for each region. So why we are obtaining in these starless cores these high values for H2CS? Well, in order to answer this question, we have to know a little bit about the physical condition of the regions harboring these starless cores. In particular, these regions are characterized by the presence of several young stellar objects, some of them being a class 3. So that means that they are affected by star formation activity, and that means that you can find winds and outflows that can affect these regions, the starless cores. So they can excavate the molecular clouds and leading to an efficient penetration of the interstellar radiation into these areas. In addition, and also is found by Silvia Spezzano in a recent work published this year, the presence of low mass star formation close to our regions is going to allow to accelerate some energetic particles and also to increase, as a consequence, the local cosmic ray flux and therefore the ionization rate. So altogether, this could lead, as a consequence, the high fractional abundances of formaldehyde that we are observing here. These results is supported also by some model results. In particular, we have considered the Nautilus chemical code. We have run 2 models fixing values for the density and the sulfur initial abundances, and we have changed only the cosmic ray values for the ionization rate. On the left, a low value, and on the right, almost a value 1 order of magnitude with respect to this one on the left. So we observe that the fractional abundances that we obtain for thioformaldehyde are here about 5 times larger than the ones obtained with the low values for the cosmic ray model. So this suggests that the higher cosmic ray ionization rate, the higher fractional abundances for thioformaldehyde. If we come back again to this plots and we analyze now the fractional abundances for the deuterated version, HDCS and D2CS, we observe that, for example, in Taurus, we obtain the highest values in those starless cores that are located more toward the north of the filament. While in the south, where we find the starless cores C10, C12, and C16, the fractional abundances are very low or simply not detected these molecules. In the case of Orion, we also observe that there is only presence of HDCS in that starless cores with the highest value of H2CS. And similar result for Perseus, we find the highest value of the deuterated versions only in the starless core with also higher fractional abundances for thioformaldehyde. And in those cases, for example, like the starless cores that are very young, like IC348, we don't really obtain emission of these two deuterated species. If we now analyze the deuterium fractionation of the starless cores that we have in our sample, we obtain this plot where we obtain, for example, values for this ratio HDCS over H2CS that are more or less between the rates 0.1 and 0.8. This range is quite high in comparison with the cosmic DH ratio that is 10 to minus 5, more or less. If we compare, for example, with results for this ratio in other starless cores done by other authors, like for example in TMC1 and L183, we also observe that they obtain similar results as our values. So what is happening here? What is the deuterium enrichment in these cold regions? Well, in this case, this is happening through or because of two main parameters. One, because of the low temperatures, and also for the presence of large neutral species that freeze out onto dust grains. So in this case, in the cold regions, deuterium enrichment is going through the reaction between this ion, H3+, with HT forming H2D+, which can interact with other molecules and then transfer deuterium to other species. This is for starless cores. What happens if we include in our study regions characterized by higher temperatures, like for example, class 0 objects, PDRs, or even star-forming massive clouds? This is the results. We observe that, well, for this ratio, HDC over H2CS have quite high values in comparison with the cosmic value. What is happening here? What is producing the deuterium enrichment in those cases where the temperature is so high? Well, we have to distinguish between two ranges. One range is with warm temperatures and another with hot temperatures. In the case of temperatures between 30 and 100 kelvins, more or less, the deuterium atoms are being transferred to molecules by CH2D+. And this is because the activation barrier of CH2D+ when acted with A2 is larger than the activation barrier of A2D+. So here we are having chemical reactions that here we couldn't have for the low temperatures. In the case of very hot regions, like for example high mass star forming clouds with temperatures higher than 10 kelvins, in these cases what is happening is that ice mantles are evaporating, releasing into the gas phase all this deuterium. In the case of the double deuterated thioformaldehyde, we see only the presence of these molecules in the coldest regions, like for example class 0 and in particular starless cores. When we study deuterium evolution, we need to take into account that the temperature is not only the main parameter affecting the evolution of these ratios. We have to consider as well effects of time. In order to study this part, what we have done is to use again the Nautilus chemical code to run different models, considering times between 1,000 and 10 to 7 years, and temperature values ranging from 7 to 20 kelvins. We have also considered densities going from 10 to the 5 to 10 to the 7, and different initial sulfur abundances, in particular from 10 to the 5 to 10 to the minus 7. So one of the first results that we obtain when we look at these plots, we see that this ratio, the single deuterated and the double deuterated thioformaldehyde, is increasing a lot when the density is very high. and also they increase when we consider a low initial sulfur abundances. Apart from that, we also see a very strong dependence of these two ratios with time. So this suggests that these two ratios can be used as a very powerful tools in order to study the evolutionary stages of starless cores. Another interesting result that I want to highlight here is that we observe two peaks in the evolution of these ratios. Two peaks at different ranges of temperatures, in particular one between 7 and 11 kelvins and another peak between 15 and 19 kelvin. So that means that we cannot use these two ratios in order to study the temperature of starless cores with accuracy, because we are not going to distinguish in which range we are in our values. Starless cores are very normally high density regions, so that means that UV radiation is going to be efficiently absorbed and it cannot penetrate. So that means that the main or maybe the unique agent ionizing these regions are going to be the cosmic rays. In order to study how these cosmic rays affect the deuterium ratios, we see that in this model, the first row is a model with a low value for the cosmic ray ionization rate, and the last row with one value that is 1 order of magnitude higher. We observe, for example, in this case, that the peak in both cases, the low and the high values, is the same, 0.54, more or less. The only difference that we obtain between the two models is that this peak, in this case of the high value for the cosmic ray, is reached at some billion years later with respect to this model. So this means that increasing the cosmic ray ionization rate slows down the deuterium fractionation evolution by a few million years. But we are going to obtain at the same time, a very late evolutionary state, the same peak. So it's just delaying the chemistry. One of the biggest advantages of having model results and observational results is that they are going to provide the possibility of study some characteristic, like for example, time evolution, or deduce some physical characteristic of the regions that we are studying. In this case, for example, I show you how we have been able to determine the evolutionary stages of the different starless cores that we have studied in our sample. Our results can be split into two groups. One group with very young starless cores, that is times of evolution lower than 1 million of years, and another group with starless cores that are a little bit older, between 1 and 5 million years. So with these results, we can deduce that in Taurus, those starless cores that are located more into the north of the filament are more evolved than most of the starless cores that are located toward the south of the filament. And in the case of Perseo, something similar. We obtained that most of the starless cores located in the northeast of this complex are less evolved than most of the starless cores located more toward the southwest of Perseus. Also, this comparison between model and observational results allow us to derive some of the physical parameters, physical characteristics of this region. In particular, we are observing here on the right part some observational results for these two ratios, the single and the double deuterated over H2CS. If we observe, for example, in this ratio, we obtain some high values for some starless cores that are between 0.2, 0.3, in particular for Taurus and Perseus. In order to reproduce the high values of this ratio, we have to consider high density models, in particular at least densities of 10 to the 6, and also we have to consider a very low sulfur elemental abundances, in particular at least 1 order of magnitude lower than the solar elemental sulfur abundance. So this is giving very important information about the degree of sulfur depletion that we have in these starless cores. Here there are some conclusions, a summary of some of the results of this work, where we have been able to determine the evolutionary stage of the different parts of the filament that we have studied in our sample. We have also deduced some physical properties of the starless cores, like for example, the initial sulfur elemental abundances, and also how the ratio of deuteriums behave depending on the characteristics of the regions, like for example, cosmic reionization rate, density, or degree of sulfur depletion. Also, we have been able to determine that these two ratios are very good in order to determine the evolutionary stage of the starless cores, but they are not so good to determine the temperature of these regions with accuracy. As I have said at the beginning of the presentation, I'm going also to introduce briefly some of the results obtained by Marina Rodriguez about the presence of H2S in starless cores. She has studied not only these molecules, also the two deuterated versions, HDS and D2S. She has considered the same sample of starless cores as in my work, and using observational from GEMS project. In these observations, she was able to detect H2S and this isotopolog, and she also completes this observation with extra observation as well from the 30 meters telescope in order to be able to detect HDS and D2S emission. So in particular, the single deuterated version was detected in 10 of the starless cores, while D2S was detected only in 5 starless cores. So in any way, I think that we have to highlight that this represents an unprecedented sample of this data for this species in this kind of sources. In those, by the way, in those cases where we have not been able to detect the presence of these molecules, we have just derived upper limits. Here I show you one of her results where you can see the values for the ratio HDS over H2S for starless cores. Here is indicated with blue color, and for another regions characterized by higher temperature, here indicated with red colors. Solid bars are relative to those regions where we have detected HDS, and bars with lines are those regions where we have just provided upper limits for HDS. If we observe first just the part with the starless cores, we observe that we obtain values between 0.1 and 0.4 more or less, that they are very similar results to the ones that we obtained considering H2DCS over H2CS. If we compare with a region with a higher temperature, like for example with this hot corino, IRAS 16293, that is characterized by higher temperatures, about 100 kelvins at least, we see that we also obtain very high values of this ratio. What is happening here? Why we obtain these high values? Well, in this case, this deuterium that we are observing here is mainly formed in by sulfate chemistry. But we have to notice as well that this result can be an observational bias, because maybe what is happening here is that we are observing the emission from the cold envelope rather than the emission of the hot core itself. So we would need interferometric observations in order to determine this issue. And in the case of warmer regions, like for example hot cores or massive star-forming clouds, we don't find presence of HDS, and we provide only upper limits that this are probably an effect of the high temperature of these regions. I show you here a study of these two rates of HDS and D2S over H2S in comparison with some of the physical characteristics of the regions that we are considering, in particular the kinetic temperatures and these ratios over versus the hydrogen molecular density. If we observe, for example, in the first row, here we obtain that the highest values for this ratio are slightly higher for the Taurus starless cores in comparison with the ones obtained for Perseus, here with a triangle, or in Orion, here indicated with squares. On the other hand, if we observe the results of this ratio versus the kinetic temperature, we observe a decrease in trend that is expected, to be honest, because everybody knows that the low temperatures favor the formation of deuterium. But by contrast, if we analyze this ratio versus the hydrogen molecular density, in these cases we don't really obtain a clear trend. What is happening here? Starless cores are very, they are, when you have a region with a high density, this leads to a high CO depletion, and therefore this favors the formation of deuterium if this deuterium is happening during the gas phase. In this case, that we are not obtaining any clear trend, this is indicating that this deuterium is forming not in gas phase, but in by surface reactions. Finally, we have also considered that it's very interesting to compare the results that we obtain for HDS in our starless cores, but also with other type of objects, and also considering other deuterated molecules, because they might share some chemistry, and also they can maybe share some formation pathways. So here, if we observe just the first part of the starless cores, we see that the results for HDS and HDCS are quite similar. Although the results for deuterated thioformaldehyde, they are slightly higher. That can be for a later, or related with a later formation of thioformaldehyde. If we include deuterated methanol in the starless cores, we also observe that the values, the range of the value, is more or less the same as the one found for HDS and HDCS. In the case of including in the study class 0 objects, we see that although the values are more or less the same, we have more dispersions. That is probably due to the lack of spatial resolution that I was mentioned before. If we now go to more like hotter regions, like for example hot cores or massive star formation clouds, we see that the results that we obtain for all the deuterated molecules, where we have results, are slightly lower than in the case, for example, for the starless cores due to temperature effects. And by the way, with respect to this maybe issue that I have mentioned about that this dispersion could be, for example, due to the lack of spatial resolution. In this study, we have included as well interferometric data in order to be able to compare with all the this data that we have obtained here. And we see that effect, that indeed we obtain much lower values in those sources where we have obtained interferometry than in the cases where we have obtained single disk observations. So this is highlighting the necessity of using a very high spatial resolution when we study chemistry, deuterium chemistry, in such small regions. In any case, this is a work that is still in progress. As I have said, it has been done by Marina Rodriguez. Here I provide you her email, so I think that if you have any question, please don't hesitate to contact her, because she will be more than happy to answer any questions. So thank you. Sorry, can you repeat?
Thank you. So just for me, I am outsider, so I don't understand, I don't follow very well. Very well, how do you arrive to the conclusion that the H2CS proceed for the deuteration proceed through the reaction of H2D plus, while H2S is through the grains, through the ices? Can you repeat the argument you gave?
Yeah, you can see here. I show you here in this plot the dominant reactions for the deuterated version of thioformaldehyde and also for H2CS. So here you see, well, this is depend on the physical characteristics of the regions, but for example, is a high density model. We see that for very low regions, that is in our case starless cores, we obtain that for early evolutionary times, we see that the dominant reaction is through H2DC+. If we go, for example, to very evolutionary stages, we see that this is not so important. It's more important, for example, reactions with CH2D plus atomic sulfur. So depend on the evolutionary stage and the characteristic of the regions, we are going to obtain some domination of chemical reactions or not. In the case of H2CS, that it was also your questions, we see that the reaction forming these molecules is for early stages H2C plus with electrons, but if we go further in the evolutionary state, in the evolutionary time, we see that other reactions, like for example atomic sulfur with CH2 and CH2D plus, CH2D, are dominating the formation of this molecule. Yeah. Yeah.
Your argument for H2S was more observational by looking at the ratios?
Yes, in that case it was observational. We have not run models yet to
No,
determine.
but can you repeat it? Because it, you tell it in 2 sentences.
Yes,
and then,
in this one, no?
But maybe you're not...
Say, you mean this one, no? That we have obtained similar observational results for the ratio for HDS and HDCS. So they are the same, more or less, range of values, slightly higher for the case of HDCS, so maybe this is because we are in an evolutionary state that is quite late, and we obtain very high abundances of HDCS rather than from H2CS that maybe is reacting with other species and leading to a decrease in their abundances.
Okay, for HDCS, you mentioned that okay, you have distinguished between the hottest regions of your sample. I suppose that these are those of Orion A, and you mentioned that they have temperatures about 100 Kelvin, but I think that these cores are very far from the densest cores. I think, do you have measured this temperature, or I wonder that the temperature could be near 50 Kelvin, but I think that 100 Kelvin is so high for these cores.
Yes, well, the temperature that we have obtained in Orion, I think that it was like around 30, 40 kelvins, more or less. Yes. So what we are talking here about the particular case of Orions, maybe in Orion KL, that they are closest to star forming, that increasing this temperature, but in this case of the starless cores, we have considered regions at about 30, 40 kelvins.
Okay, then in this slide, there for the high mass star forming regions, these are out of your sample. This abundance.
It would be here, this one.
Okay.
Is this one. This is the starless core that we obtain in Orion. We obtain only this presence of HDCS, but not D2CS, because the higher temperature with respect, for example, the starless cores in Taurus that have more, have a lower temperature. Yeah.
Okay. It's clear.
Yeah, it could be. I think they are both affecting definitely the evolution of these two rates, as I have seen before, that is not temperature, but also a time effect. Yeah.
So just clarifying 2 aspects that maybe I have not gotten properly. So here, okay, you have for the double deuterated H2CS, you have ratios between 0.2, 0.3, and if you go to the models from Nautilus, where you were having this, yeah, exactly.
This one?
Yeah. So Okay, you go up to 0.3, 0.4 also, right? For the
Yes,
golden
in
rate?
this,
Yeah,
yes,
okay.
in this cases, yeah.
This is what I was not remembering
So
correctly.
yes, sorry, because it's too small, maybe. Okay.
And for when you were showing for H2S in the deuteration, this large plot with starless, class 0, and massive stars, I think the work by Marina.
The last one? This
Yeah,
one?
exactly.
Yeah.
So when you are referring about interferometric observations, is which points are these ones to the right? Or
With the interferometric observations are not the starless cores, are regions, yes.
But are
Or-
the, so are really
So
low
really
values?
you have to compare this part that is massive with the interferometric data because unfortunately we don't have a starless core with interferometry
Okay.
in this
Fine.
study.
Yeah. Thank you.
Okay, now next speaker is Nassim Tanha.
Hello everyone, I'm Nassim Tanha, a PhD student of the University of Cologne. First of all, thank you for inviting me and giving me the opportunity to present you my work. So today I'm going to talk about my research during my PhD, which was centered around dynamic chemical modeling. And during my presentation, I will try to show you what we can learn using this kind of method about collapse. Core collapse, for example, about episodic accretion and radial mixing. Whoops. Okay. Well, no, it's not working. Oh, now it's working. Sorry. So I'm talking about among chemists, so I don't think I need to here convince you why chemistry matters the way I typically do when I speak with astrophysicists. And yet I want to start this talk by saying this statement that chemistry and physics are coupled. And it goes both ways. From one side, knowing about chemistry gives us information about physics, so knowing about molecules and their evolution gives us information about physics of star formation. But it's, as I said, it goes both ways. And I hope until the end of this talk, I could show you to what degree and what level physics does matter for chemistry. And we need to pay attention to physics when we want to model chemistry. So the fact that chemistry and physics are coupled adds an extra layer of complexity when we want to model chemistry. Because for one, we all know chemistry itself is complicated, so we have a very complex gas-grain chemistry. And to deal with that, we typically use this kind of astrochemistry codes. More specifically, the code that we have in our group in Cologne is called Shabtarzi. It was developed a few years ago by a PhD student of ours, and it's a rather typical rate equation-based code. It has a whole bunch of different gas reaction, dust reaction, but a few years ago, multi-layer dust chemistry was also added to the code. But then a whole other source of complexity comes from physics. So Chaptarzi, similar to many other this class of chemistry codes, are one-dimensional. So even sometimes when they're two-dimensional, we still are dealing with a very simplified geometry. And typically our physical models are non-dynamic, so we deal with simplified time evolution. But we do all know that this is far from true. Star-forming regions are anything but simple. They are highly dynamic, very non-symmetric. And in fact, to model the physics, we use this super sophisticated hydrodynamic simulations, these very expensive ones, which have also a whole bunch of physics involved. Okay, it's stuck again. So the idea of my work was to try to combine hydro simulations with chemistry simulations. And more specifically, I'm trying to post-process hydrodynamic simulations of a core collapse with my chemistry code Chaptarzi. Now, someone can ask me, why don't we implement chemistry in this hydrodynamic code? So we implement all sorts of physics in these hydro codes. Why not chemistry? This would be the most realistic way of doing it. And the answer is we wish. Chemistry is very expensive. A huge chemical network just takes too much time, and it won't be feasible. We just have to wait for the simulations forever. But then one can say, okay, that might be as well, but why can we do post-processing? It doesn't tell us why post-processing is valid. Because I just said chemistry and physics are coupled, why can we do a post-processing? And the answer to that is that not all reactions or species are dynamically relevant. So it is rather customary in hydrodynamic simulations to have very small chemistry networks. This famous NL99, for example, is one, where it includes only a handful of species, and these are the reactions which are the main coolants and so on. So these are the reactions which are relevant to the dynamic, and the rest we can do in post-process because those reactions do not affect the dynamic of the gas. Now we're stuck again. We have breathers in between. Okay. Let's see. Oh, please play. Great. Okay. Now, here I'm showing you the simulations that I'm working with. These are core collapse simulations done by Paul Rode, a student of ours back in Cologne. These are very low mass, and the specific of these simulations is that they incorporate episodic accretion and also episodic outflow feedback. You see this outflow bullet being shot into the gas as the simulation is going on and the core is collapsing further. So now these are the so-called SPH simulations, or smoothed particle hydrodynamics. The specific thing about smoothed particle hydrodynamics as opposed to grid simulations is that these are Lagrangian scheme, meaning the fluid element are the so-called SPH particles, and you can naively think of an SPH particle as a mass-conserving blob of gas moving about in the simulation and interacting with each other. The reason that we are specifically using SPH simulations to do this kind of analysis is that by design, SPH simulations are very suitable. Why? Because, as I said, the SPH particles are mass conserving, so there is no mass exchange between different particles. And because chemistry is a local effect, we can treat these SPH particles as being chemically independent from one another. So what I do with these simulations is that I sample the gas by sampling these SPH particles. Here I am overlaying two example particles on top of the density. And I track them throughout the simulations, and I extract their physical properties such as temperature, density, and so on, and they become the input of my chemistry code. Now, we take a breath again. No. Okay. So, density, I'm taking directly from my hydro simulations. Temperature is a little bit tricky here because these specific simulations don't include radiative transfer. So to calculate temperature, I use another code, RADAMC3D, which is a radiative transfer code. I'm not going to go into detail of temperature calculations, but if you have questions, please ask me later. And then, again, I don't have radiation field, but this is a highly embedded core, and it's fairly optically thick, so I'm putting AV1 everywhere, but this is something that can be improved in other simulations. So now this is an input and output of one example particle. Here on the right-hand side, you see the temperature and density of one particle. And this is the input of the chemistry code. On the left-hand side, you see the output, which is the time evolution of abundances of different species. And here I have just plotted 3 examples. Now, I want to draw your attention to these features here, these spiky features in temperature. So, if you remember, I said before that these simulations include episodic accretion. Episodic accretion scenario, as opposed to continuous accretion, is when the accretion happens in short outbursts. So in time intervals of about 10-ish years, accretion rate increases by several orders of magnitude, and you have an outburst of material being accreted onto the protostars, and then afterwards, basically, accretion rates go to 0, almost 0. So accretion creates accretion heating. So for short intervals of time, the luminosity increases, and it heats up the dust and gas. That's why we have these spike-like features in temperature. So each of these spikes are one accretion event or the so-called flares. I'm going to call them either accretion event or a flare from now on. And as you can see, the chemistry is reacting to these flares. So all the species kind of change, but how much they change and how long does it take them to go back to their state before the accretion event differs. And I'm going to come back to this, but this is one example particle. I have sampled the gas, as I said before. So I have sampled 70,000 particles, and I'm running this simulations for each of these particles. Here I'm showing you, this is a subsample of my sample. So here you see the trajectories, the densities, and also the temperatures of these particles. I just want to show you the diversity of the physical inputs. So I ran chemistry for each of these particles separately, and then we want to look at the collective behavior of the chemistry, so put them back again on the 3D. And as you can imagine, this is so much data, and the chemistry becomes as complicated and as diverse as the input. So we need to bin and average and so on to make sense of the data. So here first I'm showing you these plots where I have binned the particles in temperature bins. So on the x-axis we have temperature, on the y-axis we have the mean abundance in each temperature bin. And different lines are different times. So blue is always the snapshot right before an accretion event. All the rest of the colors are the times after an accretion, and each is 1 kiloyear apart. So here I'm showing you these 2 specific molecules, methanol and water, and you can see that they behave very similarly. so that after an accretion, the abundance increases by several orders of magnitude, and it remains high even after a few kiloyears. And it becomes more interesting if you pay attention to the temperature range, right? We're between something 20, 30-ish Kelvin. And these are not the temperatures we expect methanol to be in gas a lot, because we think that methanol is produced on dust and it's buried under ice mantle, and it gets into the gas phase due to thermal desorption. So, and that needs temperatures around 100, 200 Kelvin. So this is not a temperature range. But we do observe methanol in cold cores, in cold regions, and we don't exactly know why methanol is there. We have different candidates are always being explored, but we don't have a very good consensus as to why we can make methanol in gas phase in cold regions. So here I'm showing you basically that episodic accretion can be a candidate to produce methanol in cold regions, because during an accretion event, the accretion heating can heat up the gas effectively to a temperature that methanol gets released into the gas phase, but then it takes time for it to freeze back onto the dust. So we produce methanol in cold regions, basically. Now we wait again. It seems that whenever I stay a little bit long on one slide, then it lags. Yeah. And then it jumps twice. So now here I'm showing you another set of molecules, and you can see that right after an accretion event happens, it's already forgotten that it has happened. So immediately it goes back to the state it was before. So in this sense, we can talk about something like a chemical memory. So it seems that there are molecules like methanol, water, ammonia, which have a chemical memory of thermal history of the system, and there are species which do not. And it is important to distinguish them because they trace different physical properties. So this is the first and the last sulfur-bearing molecules that I'm showing you. Because methanol had this interesting feature, and it has this kind of chemical memory, and methanol was interesting for us also for other reasons. We kept being focused on methanol, so for the rest of this talk, I'm going to focus on methanol. And I'll wait here, okay. So I started then binning the particles into radio spins, so shells around the protostars. And here I'm going to show you this plot. I think I can work with it now. Okay. So in this plot here, you see the time is on x-axis, radius is on y-axis, and the mean abundance in each radio spin is on z-axis, and color bar is temperature. So before I start talking about this plot, there is a little bit of disclaimer. This plot is a little bit misleading, and I will show you why. And spoiler alert, it's because you don't see a spread. This is average. But we go into that later. But still, this plot is useful to point us at the direction that we can look at some interesting stuff. So first thing that we see in this big plot are these events. So these are the flare events. So I hope you can see this faint pink here. So these are the peak temperature, these are the accretion event, and you can see that this effect that the methanol is increased by several orders of magnitude and then slowly decreases until the next flare goes off, what we also saw before. But another thing that you can see is that this effect seems to be radially localized, right? So it happens in a certain radius, but if we go with smaller radii, we go to this region which is super spiky. It looks noisy actually, and it does some weird things. And then if we go to larger radii, it becomes all cold and a little bit uninteresting and boring, so this effect kind of fizzles out. And then here, though, we see this curious bump. So it is in larger radii. And I hope you can see it here, that the peak temperature is actually here, but this bump happened with some delay afterwards. So I'm going to go back to the slides and hope the presentation cooperates again. And I'm going to go into detail of each of these things that I pointed out to you. So first, based on where we see this effect to be the most prominent, I divided the region into 3 parts. So we first start with the intermediate region. So radii between 500 to 2000 AU, where we see this effect to be very visible. So these are the so-called violin plots. Here we look at the distribution instead of average. So, and the x-axis is time. So, and the time interval is the time between 2 flares. And blue is gas distribution, yellow is dust, and on the lower panel you see temperature. Now starting from a flare, you see temperature is raised here, and corresponding here, everything is on gas, nothing is on dust. And as we go further in time, things being removed from gas and being put on dust. So here you see we have this bimodality where some of the material is on gas, some on dust. We go further, and the methanol being removed more and more from gas until here everything is almost everything is on dust and almost nothing is in gas phase. Right. I should have come up with some jokes for this delays in the middle. So if we go to the most inner region, so the first thing you see is this huge spread, right? So the spread is several orders of magnitude. And this corresponds to those spiky region that I showed you on that plot before. So obviously those spikes are just spreads. And the reason for this is that we're going to the regions very close to the protostars. So the density is high and the chemistry is fast. On the other hand, this is a binary system and we are getting very close to the binary. So the temperature and density variation, both in time and space, is very high, meaning the physical parameters are very inhomogeneous, but also varying very fast. But chemistry is also fast. So everything is changing and everything is very inhomogeneous, very out of equilibrium. So you create this kind of big spread and mess. And then we try to go to the exterior. Right. So we try to go to the exterior, and here we are in the radii larger than 2000 AU, and you can see that the spread is completely gone, and we almost see no effect of the flare here. So this is just because we are so far away that the accretion heating is not efficient enough to heat up the gas or dust for the thermal desorption to happen. So here I'm just showing you a GIF, putting them all together. So you can compare them in range, and you can see when we go from the inside out, how the spread becomes less and less, and how this effect with methanol basically appears and disappears when we go from inside to the outside. Right. Oh, no. Okay, that was wrong. Okay, I don't know how to right-click on Mac, so I cannot loop this, but I hope it's fine. So As you can see, these are, so far I've talked about what I've shown you. I've binned the particles, so I've basically I'm smearing out anything non-symmetric in this system. So here I'm showing you a 3D distribution of the particles that I've sampled from left to right. You see temperature, densities, gas abundance, and dust abundance. So the first thing I'm going to show you is this thing that we talked about before. So here you see all these red points here. So these are material with high methanol abundance in gas. But if you look at the corresponding region in temperature, you see that these are not high temperature regime. So basically, and this is a snapshot shortly after a flare. So we can very nicely see that we produce a lot of methanol in gas phase in cold regions just because we had an accretion event shortly before. And you can also see very nicely this dual, this on and off behavior of methanol. It's either on gas or dust. So wherever it's blue, there it's red here. So there is also something else you can see. So a footnote, I'm not including outflow particles into my analysis at all because of some technical complications. But you still can see these particles here, which are outlining the shape of the outflow cavity. So these are the so-called entrained particles. These are particles which are being dragged by the outflow jets. So do you remember that bump I showed you in the plot earlier, which was in the colder region in larger radii? So we thought maybe these are basically these entrained particles which were orbiting closer to the protostars. So they were affected by the accretion heating, but then an outflow also happens and they're being pushed out. So we see them in larger radii later time. So to check that, I basically selected all the particles from the larger radii with high methanol abundance, and I looked at where they're coming from. And this is the result. So you can see that our assumption was correct. So these are the particles or the material which were orbiting closely to the protostars, and an outflow happens and then they're being shut out. So what we see is that how outflow jets can efficiently mix radially, and we can also trace that via methanol, because methanol has this property of having some chemical memory. And with that, I come to my summary. I hope I could convince you that the coupling dynamics with chemistry is useful and is important, and we can learn new things about chemistry from doing so. And that episodic accretion heating can be a candidate for production of certain species in cold regions. Some species have a memory of thermal history of the system, and some do not. The flares affect mostly the inner region of the envelope chemically, and the outflow jets cause radial mixing, and methanol can trace these entrained particles. Sorry for the lag of the...
Thank you very much for the talk. Nice to see very nice physical models being coupled with chemistry. I'll poke a bit at your assumption of AV1. So I'm a bit surprised that you're assuming this, because you can get the UV field with a RADMC3D as well. And having also done a similar, simpler physical model with also RADMC3D, I saw that the UV was very critical for the chemical process that you get out, and the UV field will be AV1 for only a small region in the system. And
I mean, the
maybe
system
related?
is also rather small, right? So I'm kind of, this is like, I'm just looking at under 1,000 AU, 10,000 AU? Or you mean even smaller.
I mean, it will be so I mean, if I plot like AV for an outflow cavity wall and I have an excavated region, then I mean, AV1 will be like a shell kind of conical thing further in, and I mean, for the other one, closer to the cavity wall, you will be more strongly irradiated.
This is something like this. These are definitely the next steps in doing so. But I should say here that the RADAM C3D, the dust temperature calculation, I think took the longest time, because it's just RADAM C3D is also a slow code. It's not parallelized that well, so it's it was rather a necessity. But actually, hopefully at some point one could do this analysis on simulations which self-consistently also calculate radiation field. I just didn't have access to those kind of simulations, but this is definitely a space for improvement there.
So maybe a quick follow-up. Do you expect that the episodic events to also come with a UV spike, actually, not just temperature?
I think so. I think X-ray. I think actually X-ray. And I tried to estimate the effect of X-ray on the flares. It didn't it didn't really work well, because the chemistry that my chemistry code does take one global cosmic ray ionization rate, so I couldn't vary it. I tried to trick the code to do some stepwise changing. Didn't really work well, but yes, this is also, I assume it will have big effect actually. There are studies on some similar, well, not similar, but like having 1D simulations with like varying X-ray field, and it should have an effect, yes. Though I'm sorry, I'm not sure if I'm not sure if it would just enhance. I'm thinking it would just enhance this effect, but I'm not 100% sure. This is something I would need to see.
My question is maybe naive. On if you can show your plot where you have your two events at the beginning, we do see clearly two different situations. One, you have only the temperature that raises and the density does not. And the second one, you have a rise in the temperature and a jump in the density. So you have two events. And so my question is, what does it mean, yes, physically? So the first one, you have a small jump in density.
These are independent.
And yes, and my question related to that, it's there is also a specific chemistry, shock chemistry, that we know is also very sensitive to the magnetic field, and so all the kinetics are sensitive to that. So could you comment on that? Because it's like a shock or a sea shock in some place.
Yes. So, so on the first question, the density and temperature here, these variation of temperature and density are independent. So the temperature spikes are happening because of the flares, but the density increases because this particle happens to go very close. So it is basically falling into, so it's orbiting very close, and it's going to fall into the sink shortly after. That's why the density is rising. So these are not related. This is just a particle. So as I showed you before, these particles take very different paths. Yes, this is accidental. Yes. we don't. Yes. So maybe so to kind of comment on both of your questions. So we don't have shock chemistry in our chemistry code, and this could raise issues in the shocked regions. Yes, but this is also one of the reasons I'm not taking the outflow particles, because our temperature estimate on the outflow particles are just very off. That's why I did not include them in the analysis.
Oh, well, I have
but the density effect will show itself in the chemistry, because I am tracing the density and temperature.
Just a question, because this is one particle, so how
Yes.
many particles are suffering a similar behavior?
Oh, you mean, so
yes,
are affected by the flares, you
yes.
mean? Good question. Wait, I can do.
I mean,
I
you
think
have
like
something like a layer, a spherical layer around the protostars.
Yes, I mean, so as I showed you, the particles which are confined in these regions are affected, right, mostly. So I'd say maybe 30,000 particles, 20,000 particles. But so the thing is, in this point, all of them are not here, right? So because these particles so some particles might be affected here, and here they were there,
yeah,
right?
My question is, are they located in a spatially correlated or something like that to be able to detect the effect? Do you understand me? But really, when you observe, you are observing different pointings, and then in order to detect that, you need that they are located at a given location in the
so
space.
you mean how much actually emission is there? Is this your question?
Yes, I think so.
So this is, I think, a whole different, it would need a whole different set of simulations that we could do afterwards. And it's hopefully would be some of the future of this work that one would do synthetic observation on these to actually calculate the emission. Because as you said, so having high abundance there, it does not tell what fraction of particles have the high abundance, yes. So this needs another set of simulations and calculation to actually calculate how much emission we could expect.
Now we have a break of how much the break? Half an hour.
Can I start? All right. Hello, everybody. Thanks for waiting on the technical difficulties. I'm here on behalf of the Pils Cygnus team at the Niels Bohr Institute in the University of Copenhagen. Lars sends his regards to everybody who knows him. So I'll be spending about maybe the first third of the talk talking about the Pils Cygnus project as a whole, and some of the latest results, and then I'll zoom in on my own work for this project for the latter 2/3 of this talk. So let's start out with what are our fundamental questions? So the first one you all know and love, the missing sulfur problem. So where does the sulfur go when it's depleted in dark clouds and hot cores and corinos? The ones that are more specific to our project, how do external factors like nearby OB stars and the initial physical and chemical conditions, how do they affect the protostellar chemistry? And lastly, how does the is this the pointer? Yeah. How does the chemistry suggested by lab experiments affect our ability to reproduce our observations in chemical models? We are taking a truly multi-institutional and multi-angle approach. So the observational data is handled by me and other members of the Center for Star and Planet Formation at NBI. Lab experiments are being conducted by the scientists at LERMA, Laboratory for Studies of Radiation, Matter, and Astrophysics, and Atmospheres. Most of that work was being presented by Francois just on Wednesday. And then both of our institutions do chemical modeling of various types. So the project that I'm representing, the Protostellar Interferometric Line Survey, or Pils Cygnus, the offshoot of the original Pils survey. It's a sub-millimeter array survey towards 10 protostars in Cygnus X. It's designed to be at have similar frequency coverage to the original Pils survey by Jorgensen et al. And the aims are mainly addressing the questions that I detailed at the very beginning. And specifically, we want to compare the chemistry to similar line scans of low-mass protostars, like the Pils Cygnus, or the original Pils target. We want to compare the chemistry to the distance from Cygnus OB2 with all the sources in the same cloud to reduce intrinsic variability. I've got a little star there because we found out after having already done the survey and taken the data that one of the sources is actually twice as far away. But data is data. We kept it in the survey. And of course, with lab studies, you want to use these sources to benchmark models of sulfur chemistry. So the Pils Cygnus targets were selected on a number of criteria. Bolometric luminosity and 1.2 millimeter dust continuum luminosity. These are mass tracers. We did not actually select them to be the biggest sources. We wanted them to be big enough, but not necessarily the beasts. So, I mean, we did incorporate N30, which you might know is W75NB. That is kind of a monster, but most of these other ones were selected a little bit more randomly. But we still needed them to have strong SiO and H2O 2-to-1 emission, which are outflow and shock tracers. And these are sort of indications of, these were supposed to be sort of indications of the presence of relatively advanced chemistry. We also wanted to make sure that there were previous, and we're also based on previous SMA detections with H2CO. These are from data, unpublished data from Kongyu Chiu. Again, we selected them for belonging to the same cloud and at a variety of relatively nearby distances to Cygnus OB2. This is the picture up here is Cygnus X North, where 8 of the 10 sources lie. So most of them are in the DR21 filament. There's this one called N12 over here, and N63 over here, and N30, which is W75, and then, come on. So why did we choose Cygnus X? Well, first of all, it's fairly nearby, not quite as nearby as Orion, but it's also not quite as well studied as Orion, although it's coming very close. It's got a lot of both high and intermediate mass star formation happening, and again, because it's near, we can resolve individual protostellar envelopes, and we can at least hope to resolve some of the hot core regions. In particular, the sources N30 and S26 were resolved at the 100K radius. Earlier surveys identified several sources with luminosities between about 100 and 100,000 solar luminosities, and not very many hot core and Corino chemistry studies had been done in that range. Furthermore, the cluster mass function, for an example from Roman Duval et al. 2010, that suggests that most stars of all masses form in sort of these dense high mass clouds, and not in the kind of environment that the original PILS target was found in. So the original PILS target was sort of a beast in a relatively rarefied environment. So Cygnus X is a little bit more typical of what we think most star-forming regions, or where the regions where most stars in the galaxy have originated. So here's a nice, these are the SMA continuum images of our sample. Again, N30, when I say N30, I'm referring to this W75NB, for those of you who are familiar with that object. S26 is AFGL 2591, which I'm sure a number of you are fairly familiar with. The rest of these are all labeled per the naming scheme of the original, of an earlier survey that first detected these cores, which was Mott et al. 2007. So the frequency coverage of the SMA survey, 62 gigahertz continuous coverage centered on 345 gigahertz, or about 870 microns. These were chosen to cover a lot of COMs, particularly the methylated species, and of course the S species and their 33 and 34S isotopologues. The resolution, with the exception of S26, it's, they're all resolved at about 1.5 arc seconds, and for all but S26, that corresponds to about 2,000 AU. We also have some supplementary data from the IRM 30 meter telescope in a couple of bands that were maximized to focus on S species and isotopologues of all of the different sulfur species, including carbon chains, methyl mercaptan, NS, HSCN, and so on. These objects, the objects that were covered in this case were just Cygnus X N12 and N30. Some of the first results were published in Ellikel et al. 2021. However, most of the analysis is still ongoing, so stay tuned. And of course, the lab work, which was discussed in much more detail on Wednesday by Francois. So the temperature programmed desorption experiments with ices of HCO and H2S in various proportions seem to, by those experiments, a new formation reaction was inferred for OCS, which goes like this. You abstract H2S to HS. Then that HS combines with CO to form HSCO, and then the HSCO reacts with another hydrogen to spit out an OCS and an H2. And again, this is all on the ice phase. This is not a gas phase reaction as far as we know. It may happen in the gas phase, but what we know, we're confident that it's happening in the ice phase. Come on, there we go. So I'd like to take a moment to highlight some of our recent results, particularly by our most recent PhD graduate, Charles van der Walt, who just graduated about a month ago. A couple of his more recent works were the first one being van der Walt et al. 21, which detailed a chemical gradient in 30, especially with respect to the nitrogen species. So all the nitrogen species are clustered down here around, all the nitrogen-bearing species are clustered down here around MM1A, whereas most of the methylated comms are up here around this VLA1 or MM1B, and then the sulfur species sort of straddle the whole line. So OCS and at CS are concentrated here sort of in the middle, but some of the other S species are at points 1 and point 3. And this is suggestive of a temperature gradient, but N30 is not what we would consider a normal hot core. So if you expect, if it were a traditional hot core, you would expect that, so all these points correspond to specific temperatures, and you would expect the temperatures to aggregate in specific areas. But you can find the different temperatures sort of scattered all over the place in no particular trend. So this column is the upper level energies of these methanol transitions and the critical densities of the methanol transitions, and on the right it's the same thing for SO2. So no obvious trends in the critical density or the upper level energies as a function of position. However, MM1A within this cluster here is known to have a disk of about 3,000 AU radius. So it's hypothesized that this gradient is due to accretion shocks onto the disk, creating a non-thermal desorption gradient. This is still very much a hypothesis. We need more resolved observations, but this is the working, sort of our working assumption for works going forward. Of course, in the following year, this similar analysis was expanded to all of the rest of the pill Cygnus sources, and pretty much all of them showed chemical segregation of some kind. The spatial distributions of methanol and the sulfur-bearing species suggest that about half of the sources are sort of traditional hot cores, where the hot core species peak at around the same position as the continuum peak, but the other half of the sources are these sort of or have shock and outflow contributions, we think, because the peak positions of the hot core species or hot core molecules tend to be offset from the continuum peak. So we think, so it's more complicated in most of these sources. There were no trends detected with projected distance from Cygnus OB2, but that in itself is a rather complicated thing, because Cygnus OB2, according to recent Gaia measurements, is actually 2 clusters projected right on top of each other. So it's rather complicated to it's rather complicated to disentangle the true distances, not least of which because we're not entirely sure where, which or if both of the components of Cygnus OB2 are contributing. There are systemic differences between the sources in and out of the DR21 filament, we think, but that could be partly observational in that it's very difficult to extract the sources from the rest of their natal filament. So most of the molecular species that were detected in these DR21 filament sources were only constrained as upper limits. So for my work, I focused on these 4 sources which had reasonably well constrained measurements and not just limits. And also because at least for a couple of these sources, I was for N38 and N54 in particular, I was not able to extract the far infrared and submillimeter continuum parameters because of confusion. Just to very quickly show the column densities that were measured in these sources. The trend that immediately sticks out is that for most of these species, the sulfur species in S26 and N30, which are not traditional hot cores, are about enhanced by about an order of magnitude compared to N12 and N63, which are more traditional hot cores. The exceptions being H2CS, which for some reason is only enhanced for N30, and then SO2, which is even more enhanced than by a factor by 2 or 3 orders of magnitude relative to the traditional hot core sources. And we're not sure why yet. So here are now I come to my contributions to the project. So this is a very brief summary of basically all of the productive work that or all the fruitful work that I managed to involve myself in over the last 3 years. The first step was applying for and getting neutral atomic sulfur observations of as many of the pill Cygnus sources as possible to complement the molecular observations. Then I went on to modeling the FIR and submillimeter dust continuum images and spectra in order to get radial temperature and density profiles. Then I added new species and reactions based on lab experiments to the KETA chemical network and formatted all of that for P Nautilus, the chemical network program. Then I sort of did a 2-step integration process to simulate these protostellar sources. First starting out with a prestellar phase where I integrated the chemical network with and without the new chemistry for 1 million years at constant temperature, density, and cosmic ray flux for varying values of the initial extinction and external UV field strength. And then for the protostellar phase, I took the output abundances from the previous step as inputs and then evolved the chemistry over freefall time along source-specific structure models, again varying the chemistry based on the model, and finally compared the results to observations. So start out with the first point. Why did we pick S1? Well, you remember the talk from earlier. And you're familiar with the idea that refractory solids and ices are potential reservoirs for the missing sulfur, but there's also neutral atomic S and other species with very weak or inconveniently placed lines. So the neutral atomic S 25 micron forbidden line is accessible with SOFIA, or it was. And so we figured the SOFIA observations can at least address the possibility of neutral atomic sulfur being a reservoir while we wait for James Webb ice observations. And JWST will also be able to, observe S1 itself and at a much higher resolution, which will be great for determining exactly where in the object this S1 is coming from. So how did that run go? It didn't, at least not in cycle 8. Of course, I didn't wait around, so I went on to the spectral energy distribution part. And this is sort of a this was kind of the expertise that I brought in from my PhD, and I was using that's pretty much the same code. I pre-process images from 1.2 to 850 microns, Gaussian deconvolved all the sources, fit modified black bodies up to 4 components, and with temperature, column density, and the dust emissivity index as the variables. And then I integrated over wavelength and column density to get the luminosity and mass. But it's important to remember these were all initial values, very approximate, and integrated over the whole source. These were only to get initial values for the next step, which was to model the sources with transfer. This is what is wrong with the font? Why did it shrink the font? Weird. Okay, so that box is supposed to be around this, not floating right down here where it makes no sense. Sorry. So I measured the sizes of the I measured the resolve sizes of the envelopes at 450 microns, assumed spherically symmetric envelopes with power law density profiles proportional to radius to the power of this index P, and then used transfer to make a model grid over the envelope masses, luminosities, density power law indices, and the envelope radii. And then I used chi-square minimization to iteratively iterate between the mass and luminosity matching for the SED, and then matching the power law index and radius to the 450 micron images. Let me just note that we did not fit data at, for the transfer part, we did not fit data at wavelengths less than 70 microns because that emission is probably coming from an inner disk where the assumption of spherical symmetry breaks down. That being said, pretty much all of the masses that we calculated this way are necessarily upper limits. Just to remind you of let me just remind you briefly of the class system for protostellar objects. We focused on class 0 and class 1. That's what all the pill Cygnus sources are. And that matters for the meta-analysis that I was able to do right before going into the chemical modeling, which is a nice way to put the Cygnus sources in context. So they land right in this sampling gap where where there's not a whole lot of protostars that have been studied in detail. And what we were able to find with this meta-analysis is that if you fit separate trends to the low and high mass sources, and you break the trend at about 100 but somewhere between 100 and 1,000 solar luminosities, and then if you then fit a single trend for all over the entire luminosity range, and then you statistically analyze the ability to distinguish those two trends, or those sets of trends, you can't. The trends for low and high mass sources separately are statistically indistinguishable from a single trend for the whole sample. That means any differences in high and low mass star formation must occur on much smaller scales, like the scale of a hot core or a disk. So now I'm going to talk about the S1 observations. I lied. Now I'm going to talk about the chemistry. So I won't spend too much time on this slide, just reminding you of the features of the of the P Nautilus chemical modeling program. I'd like to highlight in particular or draw your attention to the assumptions. The program itself assumes that the surface phase is the top two monolayers of ice, and that mantle diffusion is limited by water. So only these four atoms and molecules that are lighter than water can move. Any molecules that are heavier than water but normally have a binding energy lower than water have their binding energies in the mantle set equal to that of water. They're left alone on the surface. And we, in particular, assume coupled gas and dust temperatures. Not the safest assumption, but it dramatically simplifies the problem. And again, we assume a constant and nominal CR flux and a surface-to-mantle binding ratio of 0.4. My contributions to P Nautilus itself, rather than just the KETA network, basically, I was just updating the branching ratios and adapting the KETA model, so the new KETA model, so that it could be taken by P Nautilus. So most of my work was, most of my modifications were to the KETA network itself. I'd like to note, let me just note real quickly that it's optimized for cold, dense cloud chemistry. So most of the rate coefficients are known or extrapolated to about 300 Kelvin at the highest. So don't put too much stock in the temperature measurements that go above 300. Grain photochemistry, a lot of that was very incomplete, but we were able to infer what should be done for the rest of the species based on the species that were already included. So for surface reactions, we assume that the same rate coefficients apply as in the gas phase, but for the mantle, the alpha coefficient for calculating the rate constants was reduced by an order of magnitude for most species except for methanol, which was reduced even further. That's all based on research by Öberg et al. 2016 and references therein, particularly that cotton paper. So when I'm saying the alpha coefficient, I'm referring to this thing right here. So there's the rate constant for photodissociation, which is basically just a scale factor. The added chemistry, obviously we're adding the reactions that Francois detailed on Wednesday, but in addition to that, we also wanted to incorporate some nitrogen chemistry based on the work of, and I'm going to butcher this, Roissan. Is that close enough? Based on that to sort of help prevent nitrogen sulfide from becoming an artificial sink. So all of these arrows here are hydrogenation reactions, and if the H's don't add up, it's because it's spitting out an H2. As a result, I should note that this part does not have a counterpart in the gas phase, so NH2SH does become an artificial sink, but it's not a species that we focus on in our observations or in our models, so we're kind of okay with that for now. Running the models, I kept the grid very small at first so that I could actually look at all of the images and judge whether the results that I was getting were realistic. Basically, I only selected initial extinctions of either 5 or 10 based on the extinction maps, or the column density maps from Henneman et al. 2012. I took a nominal UV strength and an estimate from Guarcello et al. 2016 for the 2 UV values, and of course the 2 chemical networks that we played with were the default KETA 2022 network and the KETA network with the new OCS and NH2SH chemistry added. And these were, And again, and just to remind you, these are the fixed initial conditions. And the reason why these all have little Ks, the K denotes the mantle phase of the ice because potassium is not included in the chemical network. Just in case you were wondering about the Ks. Come on. Okay, so once I got to look at the actual figures from all of these models, I came up with some general observations that applied to all of the objects. The dominant ice reservoir is always H2S. That's pretty consistent with what we see on comets, disregarding the refractories. The reason I'm disregarding the refractories is because the Kita network does not include does not yet include any allotropes above S2 yet, and so we sort of use that as a proxy for Sn, where N ranges from 2 to 8. And as Guillermo's talk earlier indicated, that was a bad idea. So fortunately, I did get the network. I did get some reactions that go up to S8 from one of the members of a team that's based in Japan, and I can incorporate it. It'll just be a little bit tedious. Anyway, the second most abundant ice is OCS if we use the proposed OCS formation route, and if we use the traditional Kita network, it's HS. Where the chemistry that goes beyond HSCO, like forming HCOSH, for instance, and that photochemistry would probably boost HS back up from where it is here, because it's actually starting a bit low here. In the gas phase, the high initial extinction and high initial UV strength, that combination uniquely reduces the production of methylated COMs, and also, but it enhances formic acid and H2CS. This is not seen with lower values of either or both of the extinction or the UV field. Unfortunately, I would like to say that incorporating the new, that it was easy to see the improvement by incorporating the new OCS formation reaction. Unfortunately, the models do not constrain which of the model of the OCS abundances themselves don't seem to constrain which reaction route is better. We still favor the lab-informed route, specifically because we know that HCOSH has now been detected in the ISM, and HSCO would be a precursor. And also, HS upper limits and models from that Javier talked about earlier suggests that the HSCO chemistry should produce HS versus H2S ratio that's a little bit more expected in. A little bit more like expected in hot core-like conditions. So in the diffuse interstellar medium, this ratio can range from 0.1 to of order 10. But in more PDR-like conditions, which are fairly similar to hot core conditions, the ratio was much lower. All models consistently overproduce formic acid, dimethyl ether, and HC3N. I suspect it's because we're missing some photochemical reactions that would destroy them and convert in particular dimethyl ether back into methanol. All models also underproduce SO and SO2, which we also kind of expected because we have not included shock chemistry yet. How am I doing time-wise? Okay, I'll try to speed up a little bit. So for the source-specific, as far as source-specific observations go, we did a bit better with N12 and N63 than we did with N30 and S26. That's probably because these two objects are more deeply embedded, so assumptions of spherical symmetry and absence of outflows are not as wrong. So you kind of have to visually disregard the 5 species I pointed out that were consistently over or underproduced. But if you do that, all the other species seem to match up more or less. But that's, again, only about half of them. The only model that fits the SO abundance in 63 is probably not consistent with the physical conditions around N63, because N63 is very embedded, and the model that fits it best seems to be the least embedded and most heavily irradiated. So I would take that point with a grain of salt, or more grains of salt than the rest of these points. For N30 and S26, N30, the poor model fits to N30 were somewhat expected given the disk, the strong outflows, and the multiple continuum peaks. But it still did better than S26, which, as you can see, all of these points are missing all of the models by very large margins. Pretty much all of the models all overproduce all of the COM species and underproduce all of the smaller molecules, with the exception of H2CS. Now, as I noted before, S26 is not actually part of Cygnus X. There's this paper by Ryle et al. 2009 that took some high precision photometry data and determined that S26 is at about 3.3 kiloparsecs. So since it's not part of Cygnus X, its environment is probably much more rarefied. We probably need different initial conditions, initial density, initial extinction, possibly a much higher initial UV field strength. We don't know exactly what it needs until we try it, but that's what I'll be doing. So will I actually get to present some S1 data? Well, the good news is I finally, after many delays that were not just due to coronavirus, I learned that I am going to receive this data at some point towards the end of the summer. So we may get some detections for N30 and S26. The issue was that after the 2 corona delays, the other thing that was discovered was that the overhead calculators were flawed, and so like everybody lost at least 20% of their time, and we lost 80%. So we lost all of our objects except for N30 and S26, and those objects had their integration time slashed by more than half. Fortunately, those 2 objects, we originally had the amount of time that we applied for gave them signal-to-noise ratios of order like 100. So we think we'll still get, we think we'll still be able to constrain. We think we'll be able to get detections if there are any. However, we also learned of 2 other things in the meantime. I wish I had discovered this paper while I was actually writing this proposal, but that was an oversight on my part. The protostellar models, so at the one main detection of the S1 forbidden line was in a protostar, was in an outflow shock. On the other hand, the prestellar phases of my models suggest that atomic S might be a major reservoir in prestellar objects and very, very young protostellar objects. So in order to determine whether or not there's any neutral atomic sulfur left over or left over from a natal envelope in sources like N30 and S26, which are more evolved, we would need more resolved observations. But probably the better targets to go after with JWST if you want to determine if we want to determine if neutral atomic sulfur is actually a reservoir and not just a byproduct of shot chemistry, then probably the better targets would be prestellar cores. So I'll leave up my takeaway messages. Yeah, I'll I'll take questions now, since I'm running low on time.
I realize that you have now a new chemical network, no? That you have included new reactions.
Yes.
Have you compared with the old one to see in which species you have the greatest difference or something like that? The impact of your grading?
Yeah. The biggest difference is definitely HS. That drops, by including the new reaction, that drops by like 3 orders of magnitude. So it's a big difference. And OCS also is quite different. The new reaction boosts production of OCS by about an order of magnitude, give or take. And also the nitrogen chemistry, that boosts the production, that reduces the production of NS by a factor of a few. It wasn't quite as much as we were expecting it to change, but it does change. H2S has not changed a whole lot at all, really. I'd have to go back and see what the differences are for neutral atomic S. I know that changes a little bit. I'm trying to, but I don't remember off the top of my head what all changes there. But again, the biggest differences are in HS and OCS, kind of like we expected.
Okay. Is your chemical network public?
Not yet, but I'm happy to share it.
Okay.
Yeah, I don't see any problem with sharing it. Anyone else? Yes?
So about one of the conclusions is that you have a considerable amount of OCS in the ice.
Sorry,
Yeah. Maybe we wait a little bit.
Sorry?
I can wait.
Okay.
Well, if it's a land mower, it could take much longer than a plane.
Also, move the microphone away from your mouth.
Like
just
this?
A little bit. Yeah, like there.
Okay.
There we go. Perfect.
So according to your model, it could be that OCS is, after all, very abundant in the ice, because we have thought that the reason why you could observe OCS was due to the strong band strength of this molecule, not because it was particularly abundant. So I think it is important. It's an important result because it means that CO and SO2 might not be so abundant after all in the ice, because in the gas what we see is, as you said, very different. There is a lot of SO and SO2, more than expected. So maybe you can comment on this.
Well, maybe I should have read out my takeaway messages. The hot core, just for emphasis, the hot cores that we've been looking at are not necessarily always hot cores in the traditional sense. So we're pretty sure that non-thermal processes contribute. Or we know that non-thermal processes can contribute to chemical gradients, and we're pretty sure that that this is very frequently the case. I mean, according to our small sample of 10, about half of the time the chemical gradient is coming at least partly from processes that are not thermal, and we have not included the shock chemistry. So if shock chemistry is necessary to reproduce observations, as our work suggests, especially for SO and SO2, that means that the gas phase S species may not actually be representative of what's on the ice. So yes, it's possible that the OCS is abundant on the ice, and as well as it having a very strong band, or it could be that that what's abundant on the ice is something a little bit more complex, like maybe HCOSH, and then and then shocks happen to, then shocks or other non-thermal processes can sputter it off and break it up into OCS later. So then, yeah, so we're not actually sure whether we don't actually have a way of knowing for sure whether the OCS is really abundant on the ice or just very, very strong, or just has a very strong deep band. I think JWST would be the best instrument to. I think there's it's the Ice Age survey, I think, that's going to be doing sulfur ices. So that's the one to look for to actually answer this question as to whether OCS is really abundant or just very good at absorbing on the ice.
If I may comment on your last point, I hope you're right, because it's not only a matter of higher sensitivity, it's mainly that this region in the mid-infrared is populated with many molecules, so it's you have this overlap between bands, and that's probably why we haven't seen the presence of H2S in the spectra, because it's unfortunately overlapping with methanol bands. So this problem may still be there, even though the quality of the new spectra is expected to be much better. It's difficult actually, because also in the lab spectra you have the same problem basically. So I hope you are right. I'm not sure what's going to happen.
I personally look forward to either to including myself or seeing whoever I pass the baton to more fully implement HSCO chemistry such that it can produce HCOSH, because I think that it will actually turn out to be fairly important.
Yeah. Okay. Thank you.
I'm not sure, but maybe this region is close to a supernova remnant, a higher supernova remnant. I'm not really sure. I say that for the name that it is Cygnus X.
Oh, Cygnus X1?
Yes.
Are you referring to? Oh no, that's in a totally different part of Cygnus.
Okay, thank you.
So Cygnus X is up near the tail of the swan, and Cygnus X1 is along the neck. I looked that up just out of curiosity earlier. I'm not sure if we would be able to tell the difference between, I think unless we found stellar remnants, I'm not sure if we would be able to tell the difference between supernova-induced shocks or star formation-induced shocks. I mean, there's probably a way, I just don't know off the top of my head.
Okay. Thank you for just giving me the opportunity to give this talk today. Here? Better? Okay. Well, the results I'm going to present today are very preliminary, so I won't show you very mature work as most of the talks we've heard here. But I expect to just raise your attention to the work we are doing here with Asunción and also with the group at Universidad Complutense de Madrid, with whom I'm just spending time as a postdoc, Margarita Salas Fellow. And well, I'm going to spend a couple of minutes, first of all, just to tell you how I ended up here. Because during my PhD, I spent most of my time just developing 2 modules to study or to follow the dynamics and evolution of dust grains in an MHD code. I worked with this version of Athena. Now I've moved to the recent version of Athena++. And since I had a very limited time and resources, and well, the PhD has to be ended up at a given time, I restricted my studies to a very diffuse medium, such as a warm neutral medium, which is I consider to be representative of the most external layers of molecular clouds. So the molecular cloud envelopes, where the clouds couple to the magnetic field, to the ambient radiation field, and which are mostly ionized and with high temperatures. So the chemistry there is very different from the chemistry on the dense interiors of the clouds. But I wanted to know how this transition region was and how everything just worked. So I developed these 2 modules, and I studied how dust grains inside these envelopes, which are charged, just behaved. And I found that in these very diffuse regimes, dust grains were not coupled to the gas, not fully coupled to the gas, but they also followed the magnetic fields. And I found large variations in the dust-to-gas ratio. Of course, I just restricted my study to a very this was a 2D simulation on the left, and of a size of 1 parsec. So I found variations in scales smaller than 1 parsec, but at large scales, I have to say the dust-to-gas ratio is roughly the mean dust-to-gas ratio, just assumed to be the common dust-to-gas ratio in the diffuse ISM. But I haven't had time yet to extend my study to other regimes. That's work in progress. But I want to say that other authors working with another code, Gizmo, have also devoted a series of papers to study how dust behaves and how dust just distributes inside different regimes, in particular in giant molecular clouds. And they also find that these filaments of dust are formed even inside molecular clouds. So, well, that was the final, I'll say, idea I had when I finished my PhD. Well, variations in the dust-to-gas ratio are expected according to the models. So now, what are the effects that these filaments may produce? Not only on the observations, which of course I want to try to detect them. I try to estimate these effects at short wavelengths, especially at UV wavelengths. That was the part of the spectra where I've been working until now. But of course, dust grains are bound to produce some or to increase the rise of some instabilities. They're going to affect the turbulent state of the cloud and, of course, the chemistry. So I just, as you can see, there are many ways or different paths that I could follow once I finished my PhD. And I decided to just continue, first of all, with the chemistry that I found very interesting and very complex. So I've seen that dust is often disregarded in hydro or MHD models, or if it's included only as a neutral species, that it's only submitted to the action of aerodynamic drag, but I have already justified that magnetic fields are also important, so charged dust grains are also important. So now what we are trying to do, and I expect to benefit from your feedback today, is to try to, instead of modeling, as the very nice talk by Nassim, instead of modeling a whole collapse of a cloud to form a protostar, I'm just working with a portion of a cloud, and I'm trying to see if first, or I expect to see if variations in the dust-to-gas ratio are going to be translated into significant variations on the chemistry. But first, we're trying to see if only turbulence, gas turbulence, can explain differences between the models and the observations. Because we don't want to think at first that the models are wrong. So we have to see if, well, maybe we're not observing what the models predict because there are some effects of turbulence. So maybe we have some clumps with very dense regions where the models actually match the reality, but we can't see them because of observational effects. So that's the work we're trying to do. So our strategy is very similar to that of Nassim and of other authors. So we're trying to post-process the MHD simulations, and then I'm trying to calculate the expected spectra. So I'm just post-processing my 3D MHD simulations, and then I'm trying to post-process these post-processed simulations to have theoretical spectra that I then convolved with the beam size of a given telescope, which is the 30-meter telescope, to have the expected spectra. As a toy model, we're just trying to model where I assume the dust to be perfectly coupled with the gas, so I don't have to care about its evolution because that's very time consuming. Of course, I want to do those simulations, but I need a month or more than a month for one simulation in supercomputing facilities. So I've started with only gas because we have to also understand if only gas inhomogeneities can explain these variations or these differences between models and observations. And of course, I will extend these models in the future. So the model I've called here 0, I've taken it to be a representative of the dense interior of a filament, but before collapse, so that I can ignore self-gravity for the time being. So the less physics I have involved at first, the easier it'll be to just see how these ingredients affect the chemistry. The parameters are just those parameters typical of a dense filament. I've taken a relatively small size domain because I want to use more or less the same setup for simulations with and without dust. And with dust, I need the dynamics of dust occurs at a very small scale, so I can't follow charged dust grains in a simulation of kiloparsecs because that's physically impossible to do with a computer. I also consider this model to be isothermal at 12 Kelvin. And first, what I'm doing is just I start with a homogeneous medium, and I inject turbulence until I reach saturation. So what I obtain at the end is kind of a snapshot of a turbulent, of the insides of a turbulent molecular cloud. And once I reach this saturation state that depends on the properties of the turbulence I inject, I stop the simulation. So I've started first with transonic turbulence because I've read that, or some authors say that inside dense filaments turbulence is not expected to be supersonic, but transonic. But obviously, the supersonic case is also worth exploring. And what I find is that starting from a homogeneous medium with a given density, which I call here rho 0, we can find very dense clumps of gas, very dense in the sense that I find places where the density is higher than, or it's the double of the initial density, which are represented here as the blue clumps, I think, yes. And there are other places where we have less gas than the initial value, but less by a factor of 10. So, well, I just split these, or I computed this amount, these quantities, based on percentiles, because the density distribution wasn't a parametric function. So I decided to leave on the tails as little information as possible. So I chose percentile 1.5. So 1.5% of the densities are left on the are left on the left and on the right. So essentially all my data are inside these two values, which are relatively large. But we can see that these clumps as outliers. So we really have some places in our box where density is very, very high, and other places where there's a void of material. And we expect that these variations in the density are going to be translated into differences in the expected signal when observed from ground-based observatories. So what I do is just this 3D cube, which gives me information on gas velocity and gas density. In theory, this gas density is assumed to be molecular hydrogen because of the region I'm studying. I post-process it with Nautilus. So I assume that the dust-to-gas ratio is constant. So first, I just made this linear conversion. I haven't changed the chemical network. I haven't changed anything, so I'm just working with very simple inputs and with parameters that we expect to be representative of the torus molecular region, because we want to estimate the expected signal, and we decided just to start with torus. Obviously, the quantities can be also scaled to other regions, but the chemical models and especially the post-processing of the simulations are very affected by this choice of parameters. And I know that all of you are familiar with this because you're working every day with chemical models, but what I find is that for my range of parameters, chemistry is very dependent on age and on the cosmic rays impact rate. So I've just built a grid of chemical models for different densities, okay? These densities, all the values I obtain in my simulation are contained in these ranges, okay? And these two vertical lines are the percentiles, the 1.85 and the 89.5. So most of my data are inside this regime. Outliers are, or the tails of the distribution are here. But in any case, what I see is that depending on the age, the chemistry is different, okay? And also depending on the cosmic rays impact rate, which is a very uncertain parameter, the chemistry is also very different. So I have to, each of my cubes, I have to post-process it at least 6 times, once for each age and for each extinction value and cosmic ray impact rate, so that we can have difference. Well, maybe if we restrict our study for torus, we can choose only one age, which will be the one that best fits the data we already have. But just to be sure, we want to just explore all the different parameter space. And among the species we are studying, of course, there are sulfur species such as H2S and SO and other species. And then, as I said, once we have these cubes, so my cubes had velocity and molecular hydrogen information. Now, after the post-processing with Nautilus, I have also information on other species. And then I'm also using RadMC 3D, but for predicting the line intensities, the expected line intensities. So I've also taken as input data the molecular data file from the given database. The molecule number density comes from the first post-processing with Nautilus, and the gas velocity field is the one I retrieve with my Athena++ simulations. And I'm post-processing with RAMP MC3D the projected line sites on the 3 faces of my boxes, just to see differences on the relative alignment between magnetic field and also just to take into account several possible differences between the the column densities, which are to be different depending on the point of view of the observer. And we're just working with our 30-meter telescope efficiencies and resolution. So I just show you here some preliminary maps for the 13th CO line, which is the one I've started with. I didn't start with H2S. Maybe I could have done it, but we're just working with 13 CO, which is in theory easy to follow. So these are the results of my simulations, okay, projected on the XY, XZ, and YZ axis. The magnetic field is parallel to the x-axis, so that's why you see these clamps or these structures elongated on the x direction. But when we put the line of sight over the observer just parallel to the magnetic field, we don't see those effects. We see something different. And this obviously is going to be translated into differences in the line profiles. What I'm doing is just that. I take these maps, which have a very high resolution. It's 256 cells on each axis. But when I convolve them with the beam size of IRAM, I obtain the maps on the right. So of course, differences are to be expected. I'm only analyzing the results or the values inside. Well, I'm leaving this part outside, or I'm not studying this part because of the convolution may introduce some effects on the final densities here in the boxes, so I'm just restricting my studies here. But I won't show you the results of the line profiles for the convolved image yet, because it's something we're just exploring. But for the left image, which is the YZ map, magnetic field is parallel to the observer. The expected signal according to the models, if we take as density the initial density, the gas density, the mean gas density of the cloud, and we suppose it to be at rest, not moving with respect to the observer, the expected intensity is 0.14. But in my simulation, in the turbulence simulation, in the region where the maximum intensity is reached, which I suspect is to be here, the signal rises up to 3 Kelvin. And the minimum is very similar to the mean value, it's 0.1. So, and besides here, for these cases, you can see that including turbulence also changes the center of the line, may cause some asymmetries on the line profiles, only including turbulence. And this doesn't mean that we have several components on the cloud. It only means that our cloud has an intrinsic velocity field, internal velocity field, that we can just try to see with this. Or we want to see which is the real effect of turbulence, or the effect of turbulence, and if in fact this turbulence can explain these differences with models. And I'm afraid I've talked very quickly, but I can't conclude anything because I've just started this work. But I can tell you something about our expectations. So what we expect to obtain from this study? Well, we've already seen that in the simulation, the intensity of the line changes with the gas density. So first of all, we want to see if after convolution, these differences on the line intensities are also appreciable, and if we can just try to detect them with a telescope. Then we want to study what asymmetries in the line profiles can arise from turbulence and from the relative, depending also on the relative alignment between the observer and the magnetic field. Because the magnetic field, if the magnetic field is perpendicular as the first cases, these structures are more elongated and we're bound to see asymmetries, larger asymmetries on the line profiles. And finally, as I've repeated several times during this talk, we want to see if this disagreement between chemical models and observations can arise from turbulence, only turbulence. Maybe there's an effect coming from dust that we haven't accounted for yet. But hopefully we will conclude that only turbulence plays an important role and that chemical models are fine, just as they are. They have to be improved, but not much. And there are several things I want to explore with future models. One of them is what happens if, apart from varying the gas density, I also evolve dust, and I have different values for the dust-to-gas ratio inside my cloud. But as I said, I need to carry out simulations, very time-consuming simulations. And also we are just discussing what effects could introduce charged dust grains on the chemistry, on the chemical interaction between the ionized species, because dust grains are charged. No matter how dense the cloud, no matter where you are, there are always some dust grains that are charged. The charge, of course, depends on the ambient conditions, but that's also a work in progress. And I expect to just discuss this in the future with you. And of course, any other suggestions that you may have with respect to this work are mostly welcome. Yes. 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 Yes, so that will imply that instead of having a very simple grid of models, I will have to have a grid of models for each dust-to-gas ratio I have. So I will have a kind of three-dimensional chemical grid that I will have to interpolate. It isn't, I'm sorry, it isn't working. Now, maybe? Yes, now. No, no.
So maybe you said this and I didn't understand, so how do you do your chemical processing? You say you have a grid and you have your densities and temperatures and fixed gas ratio and so on, and then you solve it according to steps?
Yes, what I take is the 3D cube. My simulations are isothermal, so I have the gas density, gas temperature, and I simply interpolate. That's why the resolution of my grid is the one I've plotted here with symbols. So I think, or not, it's not I think, it's clear that just interpolating a value between these two, it's okay. So I obtain a given value for the gas density, and I say, well, it's this one. and I take the linear interpolation between the two nearest values. Yes. Mm-hmm.
And actually, the chemistry is time dependent and density dependent. And then you have another way, so you prepare with turbulence as like a snapshot of what you could imagine to be at a given moment.
Yes.
But then, my idea is that any point of the grid should have different chemical time because they have density story that is different. So I wonder how you can manage to say what means the time in your problem. And then I would suggest maybe different approach. I don't know, we can discuss that, but it's something that is a little bit. I'm not very comfortable with this way of thinking, but maybe it's just because I don't really understand the way you do it.
Okay, so the problem is that when just doing the numerical model, you have to start from something. And we start from a homogeneous medium. But in this case, the time evolution of the MHD model doesn't have a physical connection with reality. It's only that we need a turbulent medium. So how do you reach? Okay.
But then if you want to test the accuracy of the model has to retrace something. So as an opposite way, you could say, okay, CO is between, I take one specific condition, point 1 or point 1, and I don't care. And I would just say that even when the density has more or less CO, will it affect the line profile same way or not? And then I would like to know what would be the sensitivity of your model, of your approach to the models, because you can tell, yes, my model are true, and so I get an output, but yeah, so that's my question.
I think that it was related with the Francine's question, and it's true, you can follow the dynamics, there is a particle or something like that, and this is a more accurate approach, but by now she is doing some calculations, just taking the time, assuming that the density is fixed with that. So when she in these calculations, for example, in 1 megayear, you assume that the density in your cube has been fixed within 1 megayear. This is the first approach.
Yes, okay.
Then in your first model, you can see also how to propagate the differences between the density. So you have a dispersion in density. The question is one set of your model during the time it takes to go to a saturation, as you call, very fluctuating or not? Because that's would be a question.
Okay, yes. Well, I haven't studied the statistical fluctuations from the whole time of the simulation, but what I've seen from other similar setups is that the variations are more or less increase with time. They're not very drastic, but always when you start with an homogeneous model and then introduce turbulence, you will have very intense variations. And that's also not realistic from the physical point of view. So you can't study or take as real or as valid the evolution from that stage, because that stage is a transition stage until the point you just consider to be, okay, from this point of the simulation, it has a physical sense. But before that, it's only just numerics. Yes. Well, once you reach saturation, the differences are not meaningful, because I've tried with T and 1.5 T stop, and it's more or less the same. The distribution is essentially the same in velocities and in densities. So I think that's everything. Okay, thank you.
Thank you, Leire. Okay. But I want to take some time to make some comments and conclusions. First of all, I want to thank all of you to have here. It's really a privilege to be 3 days with this group of excellent astronomers, chemists, and experimentalists, and to be able to talk with you in person. I also want to thank Leire and David that have been working all these 3 days to help us with the presentations and with the streaming. And now I am trying to make some kind of conclusions. It is true that more than conclusion is a list of doubts or unknowns. But well, I would like to say a few things, because during the first day we see that even if we go to very, in principle, simple chemical reactions like those that Javier told us to form hydrides, we still need to improve, and we need steep ab initio calculations to be able to have a good description of this chemistry. And these simple molecules are the first step to build other more complex molecules, and then it's worthy to do that. It's also important that I have learned, I expect all of us have learned about surface chemistry, because I still remember those days in which when we go to surface chemistry, we just take the same reaction rate as in the gas phase, and then seems if it works. And now it is a very old approach thus far, because now we have ab initio calculations, for instance, those that Albert told us about of the binding energies and reaction rates, and we have also experiments that Guillermo and Francois have explained us, that now I have the feeling that we are starting to understand surface chemistry for the first time. I am really impressed, because I have not had news before of this relationship between OCS, methanol, and H2S, and how the formation of one of these molecules is being affected by the presence of the other molecules. And we have these chemical networks in surface chemistry, and all the community is going to a multidisciplinary approach, in which on one hand we have the laboratory experiments, and on the other we try to model the laboratory experiments to be able that our chemistry is good enough. After all these days, I have the impression that still we think that atomic sulfur and H2S are the main reservoirs of sulfur. And in this, about that, I was a bit worried, because of course, if we want to know the role of sulfur in astrobiology, we are very interested in organosulfur compounds, and they don't seem to be very abundant. But okay, I hope that the results of Valerio in the laboratory help all of us to detect organosulfur compounds and have a feeling of how sulfur will be involved in the organic chemistry. During the second day that we were studying or trying to link the protoplanetary disk and planets, well, on one hand, we know still our models of protoplanetary disk are 2D models, and we are not able to reproduce all these asymmetries that Roman showed us. Still, we are very bad at reproducing the chemistry of protoplanetary disk. I also thank Diego for this nice talk of how to use the elemental abundances to know the formation of planets, to learn about the formation of planets. And I think that we need to give you a more detailed description of the chemistry, of the sulfur chemistry, but the chemistry in general of protoplanetary disk in order to have reliable diagnostics for planet formation. Still, there is a big jump. I had the feeling that we now have the connection between comets and the interstellar medium. We are okay. We have some good indications that the chemical composition of comets is inherited from the interstellar medium. But, well, the link between planets and interstellar medium is still very doubtful, and we have to work more on that. And, well, we come today, and I'm also very interested in all those projects trying to link to couple the chemistry and the dynamics. Thanks, Nassim and Leire, for your talks that are a new way of understanding the physics and chemistry of the interstellar medium. Still, we have a lot to do because we know that shocks are not included. I think the sputtering is not included either. But anyway, this is much better that only a few years ago, and I think this is the way. And thanks everybody. I think we can repeat it. Well, we are going to repeat it in September in Leiden, at least a few of us, but I hope that we can meet again in a few years and we have some new, a lot of new experiments, calculations, and observations that help to understand the sulfur chemistry.